of my favorite keto people in the entire world, Dr. Benjamin Bikman.
Thank you, Brian. Thanks for the invitation. And thank you, Robin, for managing the talent so well throughout all this preparation. I'm thrilled to be here. This is a new sort of venue for a person like me. I'm a scientist and a professor, so I'm normally giving talks to other scientists, but these opportunities to speak to people who are actually more interested in science than many of the scientists I know are quite enjoyable for me. So I'm thrilled to be here. I'm thrilled in particular to share with you some of the research that I've found and have done in my own laboratory with regards to how the cells regulate mitochondria, particularly how ketones and insulin resistance play into that. And what I need to do on the front end as I go through the introduction phase of this brief talk is just hopefully give you an idea of why this matters, why the mitochondria matter at all. So I am a professor scientist at BYU, high up in the Rocky Mountains, beautiful, much better skiing than Austin. Now, I do also need to disclose very briefly, I'm involved in Insulin IQ, which is an effort to educate people. It's nonprofit. We just share information about the relevance of insulin resistance and chronic disease. And insulin resistance and bioenergetics, mitochondrial function, that's my research focus as a scientist. And I've ventured into this other space, this best fats, where we make a low-carb, high-fat shake for now. Anyway, those are the two websites if there's any interest. So let's get right into the story then. By way of introduction, the mitochondrion itself, the singular or the plural mitochondria, that's the main character in this story. And I want you to care about it. We need healthy mitochondria. All of the cells in our body, except our red blood cells, have mitochondria, and the mitochondria have to work well for the cell to work well. It is essential to normal, healthy cellular physiology and, by extension, healthy whole body physiology. The mitochondria are essential. If the mitochondria aren't working well, mayhem ensues. You'll have problems of cardiovascular health, like atherosclerosis or cardiomyopathy, the heart muscle itself actually failing. You can also have cognitive brain disorders. You can have muscle wasting or joint disorders and myriad other problems. So these are all consequences of when the mitochondria doesn't work well. And of course, of interest to most people who are on ketogenic diets, what pulls most people, and not all, but most, will be gaining healthy body weight. And so thus, many people want to talk about, I hope you do, I certainly do, and am going to, talk about the relevance of mitochondria in the context of metabolic health. Now, as a scientist, my academic background was a PhD in bioenergetics, which means I spent a lot of time trying to learn about the mitochondria, how they work, why they're relevant. But I also resent somewhat the way people talk about metabolism and metabolic function. So very briefly, let's make a common ground of what metabolic function means. What does metabolism mean? Well, metabolism is the sum of two processes happening in any cell at varying rates all the time. In other words, metabolism is the sum of catabolic reactions and anabolic reactions. Catabolism and anabolism. And catabolism are the processes that are interested in breaking things down. And of interest here, for example, breaking down lipids and glucose for fuel, the main catabolic fuels. We're breaking them down. The mitochondria is breaking these things down in order to, in the end, actually let anabolic reactions happen. But I'll get back to that in just a moment. So anabolic reactions are interested in building things up. And I just have a very simple example of that here on this little paradigm that we'll come back to from time to time. So anabolic reactions take the simple building blocks like carbon, for example, and it will turn it into a lipid. It'll turn it into a glucose molecule. It can help make new proteins. So all of these things are the anabolic reactions, coupled or matched with catabolic reactions. But how? Anabolic reactions are not cheap. It takes the cell a lot of energy to create something new from basic building blocks. So it does this by matching what a catabolic reaction creates and then using that to build or to fuel the anabolic reactions. And the way the body does this is catabolic reactions, as we're breaking down nutrients like lipids and glucose, will create a molecule called ATP. And ATP is really, for lack of a better term, energetic currency. It's the way the cell will then pay for an anabolic reaction. And so catabolic reactions produce ATP. ATP can then be used to fuel the anabolic reactions, which again, they're expensive. They take energy. They demand something from the cell, and ATP is that something. Now, in addition to creating ATP, catabolic reactions also have a few other products that are just worth mentioning. One thing is that in addition to ATP, catabolic reactions will produce metabolites. The most famous of these would be lactate, although there are others. And mind you, what did I not say? I did not say lactic acid. That's something that we don't have any of in our bodies, and no other mammals do either. So just as an aside, because I have to be a diligent professor, blaming muscle soreness on lactic acid is as erroneous and mythical as saying that it's the little microscopic unicorns poking my muscles. It's not. There's nothing valid about that. So lactate, other metabolites are also produced. But interestingly, and we'll come back to this later, heat is also produced from reactions. No reaction is perfect. Some of that imperfection is manifested as the chemical reaction giving out heat. And that we'll come back to why that's relevant in just a bit. So one last difference between catabolic and anabolic reactions that is relevant is where it happens. Whereas catabolic reactions predominantly occur within the mitochondria, anabolic reactions primarily occur outside the mitochondria. Okay, so which event predominates, catabolic or anabolic within the cell? We don't want both to be happening at the same time. That would create what's called a futile cycle. If the cell's building something up and then only to break it down, and then to build it up again, and then to break it down again, that wouldn't be wise. The cell's designed better than that. So we have a way of determining which one will go, and insulin is the key regulator of this. There are other signals, but insulin reigns supreme. And one of my academic heroes, George Cahill, talked about this a long time ago. Not that long, right? Thank you very much. 71 in this paper, where he noted that insulin was the key controller regulating how fuel was used in mammals. And so, in other words, insulin's going to decide, is the body going to store fuel or is it going to use it? And of course, someone who's interested in weight loss is interested in the body using fuel, not storing it. So, to be precise, when insulin is elevated, the body cells are primarily going to be in an anabolic state. It wants to build things up. It wants to make glycogen. It wants to make fat to store. In contrast, when insulin is depressed or when insulin is low or basal at normal fasting states, the body will primarily be more catabolic. Now, it's not just insulin involved on that catabolic side. Glucagon itself can induce catabolic reactions, and that's sort of an opposite hormone of insulin. And then the fasted state as well, genuinely not eating, not taking in calories. And that's a state typically identified as a low insulin to glucagon ratio. In other words, insulin is low, glucagon would be high. Now, in the same state, we also have this magical process known as ketogenesis. In other words, the liver, if insulin is low, the liver begins producing ketones. And this is a state that whether you're eating low carb, high fat, or truly not eating anything, ketogenesis is what typifies a fasted state, that low glucagon, that low insulin to glucagon ratio. And that's one of the one of the beneficial properties of a low carb ketogenic diet is that you're getting the same hormonal milieu of a genuinely fasted state, and yet you're not actually depriving the body of energy, but you're getting the benefit of that. Okay, so let's look very briefly at ketogenesis before we move on. Ketogenesis can only happen when insulin is low. We are finding ways with supplements to sort of bypass this fundamental biological principle, but normally ketones should only be high because insulin is low. Now, when you're taking a ketone, that's a different story, but when you are ketogenic, you are ketogenic because insulin is low. And as an insulin resistance scientist, that's how I first came into this space. I came into it not because of the ketones themselves, these magical molecules, but because I have a great appreciation for insulin. All right, so when insulin is low, the mitochondria within the liver in particular are chewing through fatty acids as fuel, breaking them down very readily. We get a lot of acetyl-CoA, and then acetyl-CoA is turned into ketones, the ketones that we all here know and love. And ketones are remarkable. They are a very viable, good fuel for any cell with mitochondria, including the brain. They also are themselves viable signaling molecules, and we'll talk about some of that. They're telling the cell to act in certain ways. And they are evidence of a fasted state, whether you're actually fasted or just somewhat tweaking your macronutrients enough to appear to be fasted. So that's all introduction. I've introduced you to the three key players being the mitochondrion, insulin, and ketones. And so let's now delve deeper into this and talk about what happens to mitochondrial regulation in states of elevated ketones or elevated insulin. Now, one note, when I'm talking about as we go through, we'll define what I mean by mitochondrial regulation and mitochondrial physiology. And we'll look at how these regulate mitochondrial number, how they regulate the shape or the morphology of the mitochondria, and then how they regulate mitochondrial function. We need healthy mitochondria for healthy metabolic function. So when I talk about insulin, what I mean to be saying, and hopefully I will say, hyperinsulinemia and or insulin resistance. Insulin itself, we need. We were built to have insulin in our bodies, and we need it. If you don't have it, it will be lethal. And that's why a type 1 diabetic has to have insulin injections. We need it. And insulin in good, healthy amounts in a good insulin-sensitive body is doing what it should, even affecting mitochondrial function. We just need to keep it working well and not too much of it. So when I'm talking about insulin in this lecture, in this talk, I really mean to be saying hyperinsulinemia and or insulin resistance. So first one, mitochondrial number. Depending on the state of the cell, a cell can undergo something called mitochondrial biogenesis. That's when it's taking the mitochondria that it has within the cell and then multiplying them. In this, there will be states like, for example, adaptation to exercise where we need this to happen, or a muscle cell needing to use more fat for fuel. You have to have mitochondria, even to use fat and ketones. Both of those catabolic processes need mitochondria. This primarily is happening through the actions of a master mitochondrial protein. And I hope I'm not getting too deep here. But if I am, pretend you're my student and you just have to suck it up. I'll start to get disappointed if I see your heads go down to your phones, but I'm used to seeing that, so I shouldn't be too disappointed. So in this case, PGC1 alpha is the key to mitochondrial biogenesis, and wouldn't you know it, insulin has a somewhat abusive relationship with PGC1 alpha. When insulin comes to the scene, it is directly inhibiting PGC1 alpha. And so as insulin starts to climb in the body, due to lifestyle primarily, and a person is becoming insulin resistant, this process starts to shut down. And the amount of mitochondria will diminish, or a cell's ability to create mitochondria will be diminished. Now that's not too surprising. Remember, insulin is interested in anabolic reactions. And these are reactions, whether it's creating glycogen, creating lipid, like fatty acids or cholesterol, those are happening outside the mitochondria. But be that as it may, insulin inhibits mitochondrial biogenesis. And there are multiple lines of evidence to support that. That top study in particular, prolonged exposure to insulin suppresses mitochondrial production in liver cells. Now, what about ketones? Now, when ketones are elevated, and I sort of already let the cat out of the bag here, ketones will activate PGC1 alpha. It's stimulating this master mitochondrial regulator, and thus the consequence is expected. When ketones are up, PGC1 alpha is active. That means the mitochondria begin to replicate. They start to reproduce, if you will, and we have this process of mitochondrial biogenesis. And this is very well documented in literature. And it's not surprising, not only do we make ketones from within the mitochondria, we also use them. So just for ketones to be used, as I said earlier, a cell or any cell needs mitochondria to do that. And as I said, a lot of evidence to support this effect across multiple publications. Now, wait for the human data. It'll be coming soon. But a lot of evidence already in cells and rodents, human data forthcoming. So this one brief immediate conclusion with regards to mitochondrial number, hyperinsulinemia, insulin resistance suppresses mitochondrial biogenesis. And so if you're a person who's interested in chewing through, catabolizing your own fat, if you're insulin resistant, your insulin is this hyperinsulinemia is working against you, at least initially. So it needs to be corrected. In contrast to hyperinsulinemia, ketones, elevated ketones, are promoting mitochondrial biogenesis, providing a more favorable milieu to be catabolizing nutrients. Okay, mitochondrial morphology. This is a concept that might not be, at least initially, overly appreciated, but it's relevant for healthy mitochondrial function. Anyone who's seen a picture of a mitochondria in a textbook would look at the mitochondria as something like this, a small sort of circular or kidney bean shaped organelle. That's a word for the other things in the cell. However, this is an image from my own lab where students, my undergraduate students, they took muscle cells and stained the muscle cells. They affixed a certain molecule that will bind to mitochondria and then fluoresce a certain color, in this case red. And if you can see up there, you'll see that those little red lines are the actual mitochondria within the cell. And that doesn't really look anything like a small little blob, right? It's not a small little dot. And in fact, we've known that for a long time. The word mitochondria itself partly derives from the Greek word for thread. That was not me. So mitos means thread. Now, I'll just go on and I'll speed through this then. So the mitochondria can either be a distinct little divided mitochondrion, or it can be that long, stringy, reticular mitochondria, where it is, you take several little mitochondria and you join them together. That process, that dynamic process, is in fact something we refer to as mitochondrial dynamics, whether the mitochondria are undergoing fission or whether they're undergoing fusion. That's something that is very intimately regulated within every cell. And insulin itself, in healthy normal levels with healthy signaling, plays a very physiologically relevant role there. However, in hyperinsulinemia and insulin resistance, we drive that too far. We end up pushing and forcing the mitochondria to be more in a state of fission. It's forcing this fission. It's forcing the mitochondria to pull apart and to stay separated. And in the end, this has very demonstrably negative effects on the cell. Not only can the cell not produce ATP as well as it could before, this fundamental molecule for helping a cell work and do its job, it can also induce insulin resistance, which is very much related to the studies that have shown increased weight gain. And it also increases oxidative stress, something we'll talk more about in just a minute. Here's one study that mentioned, you'll see that highlighted line there, hyperinsulinemia increases mitochondrial fission, in particular, this fission protein, dynamin-related protein 1, DRP1, and we'll come back to that in just a little bit. So what about ketones? What are ketones doing? Well, whereas insulin resistance is very well established to be forcing a state of fission, mitochondrial fission, with ketones, we don't know. This was a very relevant quote from articles I could find where they're saying the role of ketogenic diet to impact mitochondrial dynamics is limited. Well, the nice thing about being a scientist, if I see that there's no answer to something, I'm going to find it. And so I got the students together in my lab and we laid out some experiments. So we experimented in what happens when we treat muscle cells with ketones and what happens when we induce ketosis in an organism, in this case, rats. Now, one note, and Amber may talk about this more in just a bit, it is hard to get almost, to my knowledge, any other mammal except a human into ketosis. Look at the diet we're giving these rats, a 90% fat diet, 1% carb, and yet their ketones go up about 25% in compared to the other group. If you put a human on a 90% fat diet, their ketones will go up 10%, at least, 1,000%, 10 times higher, even more compared to a high carbohydrate fed human. So nonetheless, we induced this state of ketosis, albeit somewhat subtle. And what we found, and what data that I'll show you, we looked at these two proteins that regulate fusion or fission, mitofusin 2 or DRP1. And what we found with the muscle cells, we treated some muscle cells growing in a funny little dish with just normal culture growth medium, and some with ketones. And we looked at these two proteins, and we found that the cells that were treated with beta-hydroxybutyrate had significantly more mitofusin 2, suggestive of an overall shift towards greater mitochondrial fusion. We'll confirm this with more experiments soon and actually look at the mitochondria. And with the ketogenic diet-fed mice, or rats, we had the standard chow-fed rats, the ketogenic diet-fed rats, and we took their gastrocnemius, which is a mixed muscle down in the lower limb. In we have a gastrocnemius as well. It's the big thing that, well, some of us bigger than others, this medium-sized, smallish thing on me, on the outer part of your calf. It's the outer part of your calf, whether it's big or small. May mine someday be big. So we looked at the proteins there, and we found generally a similar trend. In fact, just the same trend, where we had much more mitofusin 2, suggestive of greater mitochondrial fusion in the presence of greater ketones in the muscles of these animals. And we'll confirm this study again by actually looking at the mitochondria in the near future. So the conclusion from this little part was that hyperinsulinemia and insulin resistance is inducing mitochondrial fission. Ketones are promoting fusion. Now lastly, mitochondrial function. We'll define this as two things, because function is a very broad term. Oxidative stress and the status of mitochondrial uncoupling, and I'll emphasize why that matters. But with oxidative stress, we look at the balance of how much a cell is a mitochondria, how much they are producing reactive oxygen species, that's that acronym ROS, versus how well the cell can defend itself against reactive oxygen species, or the antioxidant defenses. So in general, what happens in the cell, catabolic processes will break down nutrients and provide ATP. Sometimes that gets a little mucked up, and you end up producing the superoxide radical, the first of the reactive oxygen species. And this can damage the body. As we're producing too many within the cell, we can have damaging DNA, which has effects on genetic gene expression and protein expression. We can damage cell membranes. We can oxidize lipids. We can oxidize proteins. None of these things are particularly good. Thus, it's not surprising that we have a way to get rid of them. And that's the antioxidant defenses, which can come to the rescue. And if we have too much ROS, the antioxidant defenses will put them in their place and get rid of them, and thus helping the cell continue to work well. Now, in a hyperinsulinemic, insulin-resistant state, there is more oxidative stress. That's really well known. But let's look at these two balances, these two components of oxidative stress. In the case of insulin resistance, this first study is quite interesting, where they find that they took little pieces of blood vessels and incubated them with different doses of insulin. And you'll see in that small little chart, the higher the dose of insulin, the greater the production of reactive oxygen species. It was what we call a dose response. More insulin led to increased production of reactive oxygen species. And then in contrast, where you have an organism, a system, a cell with too much insulin or insulin resistance, we have these mechanisms that are in every cell, the antioxidant mechanisms. These are 3 enzymes right here that I have in that little table. And again, these are the things that are coming in to get rid of the oxidative stress. And what we find with insulin resistance, we don't have enough. We're getting depleted. In fact, that bottom one mentions it quite well, a depletion of antioxidant defenses. And these are some examples of research supporting the connection between insulin resistance and, in one, just hyperglycemia alone. What about ketones? Well, ketones, in fact, have pretty remarkable benefits when it comes to oxidative stress. One, ketones actually are used as a fuel and result in fewer reactive oxygen species being produced. So that's why some have referred to ketones as a clean burning fuel. And if you say that in the context of you don't have as many reactive oxygen species produced, that's absolutely valid. As a scientist, I could nod my head at that. And then to complement that, not only are fewer ROS produced, we actually have a more robust ability to defend the cell against them. where we have, in particular, ketones activating the mother of all antioxidant enzymes, glutathione peroxidase. This is something ketones are doing readily, thus overall creating this very favorable state. Now, lastly, in this regard, coupling status. Mitochondrial coupling. Very briefly, what do I mean by that? Here, we have this same metabolic paradigm that we looked at earlier, where we have catabolic reactions breaking down nutrients. Normally, the cell will only break down nutrients insofar as it needs ATP. That is coupled. However, sometimes mitochondria will break down nutrients not because the cell needs ATP, but just to create heat. That is referred to as an uncoupled mitochondrion, or those are uncoupling reactions, or the mitochondria are uncoupled. Now, both of these are helpful. They both occur on the inner mitochondrial membrane through a process known as the electron transport system. And someday I would love to get into that in more detail, but it's not worth it. So both of these are helpful. Whether the mitochondria are coupled or whether they're uncoupled, there's a place for both of them. But which is better? Because you have to do one or the other? It depends. And it kind of depends where we're talking about it. The skeletal muscle, which is moving us around, very metabolically active. Adipose tissue, which is where we're storing energy, not metabolically active. Let's look at those two tissues. When insulin is high, we see that adipocytes, fat cells, their mitochondria are more tightly coupled. In other words, insulin is telling the fat cells, only use as much energy as you need to produce ATP to just get your job done. Don't use any more. In other words, store. Be very miserly, be very stingy with your energy. But in muscle, we have no effect. Muscle mitochondria continue to work just fine. Now, in contrast, ketones, while they similarly have no effect on muscle, they have a pretty remarkable effect on adipose tissue. And all of this is results from my lab, all coming out in publications soon, where ketones are telling the adipocyte mitochondria, hey, be more uncoupled. Pull in, break down your lipid, break down your glucose, not because you need to produce ATP, but because you just are gonna create heat. And that is manifest in an increased metabolic rate. Some of this so-called metabolic advantage of a ketogenic diet. Human evidence coming soon. So the summary. First summary, the first conclusion from all this is that ketones are promoting a state of enhanced mitochondrial biogenesis, better nutrient catabolism, better athletic performance. Presumably. I mean, the safe assumption is very well established in research. Whereas insulin resistance and hyperinsulinemia are reducing mitochondrial biogenesis. Second, ketones are promoting an overall state of mitochondrial fusion, whereas insulin resistance and hyperinsulinemia are forcing the mitochondria apart and forcing this state of sustained mitochondrial fission. And then lastly, ketones are inducing an overall favorable state of mitochondrial function, improving oxidative stress, and improving this sort of favorable state of mitochondrial uncoupling in the fat tissue. Whereas insulin resistance is increasing oxidative stress and making the mitochondria spare energy, less reluctant to waste energy. So in other words, more of a storage mode. Now finally, I want to say as a scientist, it's fun to learn, but I enjoy sharing it. I'm a scientist who wants to share this information with non-scientists or people that aren't in the field. And I do that through social media. If you have any interest in staying up to date on these sorts of topics, I invite you to find me on social media. And with that all said, I would love to answer any questions. Thank you for listening. Please, I'm a professor. I love questions.
So you distill down such complex concepts for laymen, and it's really great.
I hope it was, really.
So one quick question is that CoQ10 is an important driver of energy production by the mitochondria.
In the electron transport system.
Right.
Right.
So what is your feeling? Because statins are the #1 inhibitor of CoQ10. So would you give the audience a little idea about how statins can interact and affect your metabolism by affecting CoQ10 or ubiquinol?
Yeah, absolutely. In fact, these were experiments done in one of the neighboring labs when I was getting my PhD. So, Nader, is that you, right?
Yeah, that's me.
Yeah, so you guys actually, I can't see you well. You probably can't see me well because of the glare. But it's my halo. It's my halo. So yeah, statins inhibit cholesterol production. CoQ10, as Nader is mentioning, CoQ10 is one of the key molecules allowing the electron transport system to work. When I was talking about uncoupling and coupled mitochondria, all of that's, CoQ10 is critical to that whole process happening. However, CoQ10, like vitamin D, like multiple hormones, sex hormones, and other hormones involved in salt control, they're built from cholesterol. And so multiple studies have shown if you take statins, you have less CoQ10, and you have a disruption in the electron transport system, usually resulting in enhanced production of reactive oxygen species. Now, many physicians try to mitigate that effect. They'll give the patient a statin, and then what will they also have them take? They'll have them take CoQ10 to try to bypass that. And in fact, there does appear, or to try to mitigate that effect, there does appear to be some evidence that at least in muscle cells, taking CoQ10 with statins can help negate, to a degree at least, that negative effect of the statins. Now, mind you, there are many other negative effects of statins too, but the obliteration of that CoQ10 pool is one of them that's just not often talked about. Wonderful question.
Hi, thank you for your amazing work.
Yeah, good, thanks, good.
I had a question about oxidative stress, actually. So you talked about glutathione reductase and all of that, and my question was, is there a way to measure mitochondrial uncoupling? For example, like we have our Q test for energy production from macros. So do we have something similar for efficiency of the mitochondria?
Yes, in fact, I didn't show those data. There are tests, but none that you guys can do, I'm afraid. And even for me to do, I would have you come in to the lab. We would pull out a small piece of your vastus lateralis. I'll do a little muscle biopsy, and then we would actually measure the rate at which your mitochondria are using energy. The rate at which they're using oxygen. And that would be our way of assessing the uncoupling status. So that's how we do it in the lab. The easiest, there's no way to do this at home. The only way that would be most relevant to the whole body would be your resting metabolic rate. Or maybe your body temperature. If you had a thermometer, a thermometer capable of really finely determining your body temperature, if you are more uncoupled, your body temperature will be higher. Your metabolic rate is higher. But not easily done. But the closest way you could do that at home would be, mind you, but body temperature changes in gals, frequently. Every month, body temperature is changing within the month. And so I'm telling you this, but the scientist in me is saying, Ben, that's not gonna work. And it probably won't.
Thank you.
Yeah, sorry for the disappointing answer. Yeah, thanks guys. By all means, find me. I'd love to talk more about this. Thank you very much.
Thank you so much.